Good morning, class.
Good morning, Professor.
That's a little better. It's a little better. Okay, so this is our first crowdsourced lecture of two. I went through the crowdsourced document, but the most popular thing, unless somebody had just held down the plus key, the most popular thing was to learn something about cosmological observables. So I'm going to take this lecture and I'm going to walk through how we do cosmological inference in a large-scale structure project. So we're going to imagine we have a large-scale structure survey, and we're just going to talk about how we do the data analysis there and what choices we make. That will touch on a few things. It will allow me to mention likelihood-free inference, although I won't talk about it in detail, but I can at least mention it. It also lets me mention, if we get there, of course I'll almost certainly run out of time, but if we get there, it lets me talk about blinding and reproducibility, which is something that the cosmological community has been thinking a lot about. And it also lets me talk about some other thing I was going to talk about. But anyway, so I've crossed off on the brainstorming document, I've crossed off topics that are coming into this lecture. But the brainstorming document is still open. I will decide at 5 a.m. tomorrow what I'm talking about tomorrow. I decided at 5 a.m. this morning what I'm talking about this morning. I'll do the same tomorrow. Advantage of jet lag. Okay, good. Large scale. Well, you know, astronomers, we have to time shift all the time because you go to the observatory and not only is it in a different time zone, but you start work at sunset. We astronomers are supposed to be good at time shifting. Okay, good. I'm going to talk about a large-scale structure survey. I've spent a lot of my life doing large-scale structure, but I'm going to talk very generally about how it works. The situation in large-scale structure is changing very fast because the data are getting much better and computation is getting much better. So we are taking far larger surveys. We now have many surveys that have more than 1 million galaxies or objects in them, Lyman alpha forest clouds or whatever. There's lots of different data sets that are now much more than 1 million objects, and we have the capability of doing simulations that are almost as big as the survey volumes, and the survey volumes are getting almost as big as the universe. One side comment is, in large-scale structure, there literally is a finite amount of information inside the Hubble horizon, and so because the universe is finite observationally, and that means that at some point in the future, we will actually know everything you can know about large-scale structure. We literally will have measured it all, in the way that in cosmology we already have measured it all when it comes to the primary CMB, the cosmic microwave background. The primary CMB, meaning the temperature anisotropies, have been measured as well as they can be measured at a wide range of scales. There's no more information there to be got. All new CMB experiments that are being done are going to polarization, to secondary anisotropies, foregrounds, all sorts of other things. The primary CMB is done, and in some point in the future, the primary large-scale structure will be done. There really is a finite volume, which is kind of amusing that in cosmology, we might actually be able to kind of end certain observational things in cosmology, and that's one of the things we're working on. Yeah.
Sorry, this is a dumb question, but when you say we might eventually have all that, are you talking time scale? Decades, centuries?
The question is about the time scale in which we might have it. We already have a substantial fraction of the Hubble volume measured on a very large range of scales. Something on the, I can't tell you a number because it keeps changing, but it's of order 10%. Okay. And we're surveying faster every year. So if it was a priority of the cosmology community to map the entire Hubble volume completely, we could have that done within 10 years. Now, it is, in fact, the cosmology community is more focused around specific science questions rather than building the complete map. I actually think the cosmology community might be making a small mistake there because, of course, the more you map, the more likely you are to find interesting anomalies or complexities. So I'm actually pushing towards more mapping in my own work, but because the community is focused on particular problems, that there isn't currently a move to map at all. But it could be in a decade if it was decided to do that. I also work on projects where we try to measure the position and velocity of every star in the Milky Way. That's another thing we might be able to successfully achieve within the next couple decades. Okay, good. Let me just walk through a kind of standard cosmological large-scale structure analysis, what it looks like. I'm not going to give you references as I go, but I'll use the terminology, so if you want to drill deeper, you can follow the terminology. Before I start, who here has taken a PhD level or graduate level class in cosmology? Okay, good. And who here has actually done some research in the area of cosmology? Oh, good. For those of you who don't have much background in cosmology, I will say some things which will be like, what? And I won't be able to I can't summarize all of cosmology in 75 minutes. So you'll just have to trust me on certain things. I will try to answer questions as I go. So don't be afraid to ask me questions, even questions that you think might be dumb questions. But I might, for some questions, just push them. Okay, good. So in large-scale structure, so I'm going to talk about large-scale structure. And of course, the idea is the universe starts in a homogeneous state, and things collapse because there's gravitational attraction, collapse into structures which you can think of as being not exactly galaxies, but collections of galaxies and voids and so on. There's all sorts of structure. So large-scale structure is the area in which we study what the current state of the universe is, or the state of the universe in redshift slices as you look back through time, and try to understand the dynamics of the universe, the initial conditions and the dynamics of the universe by looking at that stuff. So that's what we do. One of the reasons I'm using this as an example is it was thumbed up a lot in the document, but also it connects to dark matter. In fact, the most detailed things we know about dark matter come from this direction of research. So we know lots about the dark matter from a lot of different directions, but the most precise measurements of the property of the dark matter come from large-scale structure experiments. The present day, and that's how we know the initial conditions of the dark matter, and we know that it is on large scales, cold, non-interacting, and all those things you've heard, cold dark matter and so on. Okay, good. Good. In large-scale structure, the fundamental data, I should just check my notes. Yeah, good. The fundamental data are positions and redshifts of galaxies, or quasars, or quasar absorption lines, or it can be all sorts of different things, but let's think of it as galaxies, because that's the simplest case. It's the positions, it's celestial positions. So if you're an astronomer, you call them RA and DEC. But these are the angles on the sphere. So you can think of them as theta and phi, if you like. So the direction of the galaxy, and then the redshift of the galaxy. And redshift is always Z, and the redshift is related to the distance of the galaxy, right? Because the universe is expanding, so everything's redshifted, and the more distant things are redshifted more. Right? So we don't get to measure distances directly, we only get to measure redshifts directly. Okay, those are the fundamental data, and so we'll have many, many galaxies N. And N here is of order 10 to the 6 for the biggest projects that we work on. As was mentioned 2 days ago, I've worked on every phase now of the Sloan Digital Sky Survey. The Sloan Digital Sky Survey was the first survey to get into these numbers. And I was involved in the imaging part, because the way you do these surveys, I mean, if you go technically, the way you do these surveys is you take imaging of the sky, you select targets for spectroscopy, you take spectra of those targets, and from those spectra you determine these redshifts. So you use imaging to get the locations of the targets on the sky, and use spectroscopy to get the redshifts. There are many other ways you can do large-scale structure, but this is the standard way. Good. And this fact that this is 10 to the 6 is relevant to things we're going to say in a minute. Now, that's the fundamental data. What's the fundamental theory? as I said, there's this cold dark matter theory, which has a method for creating initial conditions, which is a Gaussian process. So the initial conditions of the universe are a Gaussian process. Then there's some atomic physics that happens in the very early universe that has a small effect on how things operate. And then from then on, it's just gravitational collapse, essentially, from the initial spectrum of fluctuations that were created by this Gaussian process. And then there's some details about isocurvature and adiabatic, and there's a lot of details. And if you want to study, if you want to really understand this fundamental theory, this is a lifetime, not a 75-minute lecture. But the cleanest part of the fundamental theory is the gravitational part of the theory, but then within that, galaxies form, because the things we observe here are not the dark matter structure. We observe galaxies which inhabit the dark matter structure, and we don't fully understand at this point how galaxies form. We have a general picture, but we don't have a very precise quantitative picture. So this fundamental theory is a set of beautiful ideas in gravity and a bunch of unbelievably dirty simulations that include approximations in gastrophysics and effective models that aren't even effective models like you all talk about effective models. They're like way effective. So it is now the case, because it is important, because we're observing the galaxies and because in detail it depends where the galaxies lie in the structure, the fundamental theory is horrendous simulation. Gone are the days that you calculate something by hand in cosmology. It's long gone. And it's because at this scale, the questions you can ask are so precise that you need to precisely understand where the galaxies form in the structure, and that means you need a horrendous simulation that includes the formation of the galaxies. Good. So the question is, how do we do inference in this situation? We need to remember we need to write down a probability for the data given the model. Yes?
Isn't there a theory that you feed into your simulations? Like there's all the assumptions about the way things work that feeds into that. So that there is an underlying theory, we just can't do calculations without using horrendous simulations.
Good, good. The question isn't there really like some fundamental ideas inside this thing and it's just that it's hard to do calculations and there's some straightforward parameters? The answer is yes, that's absolutely correct. The point is that even though there's a small number of parameters, we actually now know from these projects that there's actually a relatively small number of parameters that govern the whole formation of structure in the universe. There's only kind of 6 really important parameters. The theory is not computable without this monstrous simulation. And what does the monstrous simulation produce? It produces an instance of the universe, which you might want to compare with our instance of the universe. And then you can do another simulation and it will produce another instance of the universe, which you might want to compare to our universe. But notice that this is a 3 million dimensional space. And this is producing a 3 million dimensional point in that 3 million dimensional space, which is going to be nowhere near this point in general. So if you think about it, there's no way for us to write down a likelihood function. We can't write down a likelihood function. Now, there are some cosmologists out there working on writing down a complete likelihood function for this. In fact, I'm involved in some projects to think about that question. Could we write down a likelihood function for this, given that our theory is this? A lot of people are thinking about that. But right now, that is currently impossible. No one's even close. So there's various possibilities here, given that you have data and you can simulate the data, but you can't write a probability distribution over the data. Another way to think about it is, if I wanted to have a probability distribution over these, a likelihood function, right, is a probability distribution over these, that would be a density in 3 million dimensional space. And remember I said that it's hard to do densities in dimensions larger than about 12. 3 million is larger than 12. So that's another way to think about it. You'd have to do something like 3 million factorial simulations if you wanted to fully sample that density distribution, and 3 million factorial is a really big number. Love that. It's one of the few places that factorial comes up in my research. Okay, good. So now let's talk about what your options are. So one option, which people are getting very excited about, but no one has really executed yet, in fact, I'm on 2 papers that execute close things, is something called likelihood free. This is an option. I'm going to put it in parens because I'm not really going to talk about this. The idea of likelihood-free inference is exactly this problem. You have simulations, you have data. You need to somehow ask, what parameters for the simulations do your data suggest? And likelihood-free inference is a way to obtain a proxy for the posterior over those parameters, even though all you can do is run simulations. And this set of methods, it comes by different names. It's also sometimes called ABC, and I think it's also sometimes called implicit. This set of methods is very exciting, right? There's been a lot of work on this recently, and part of the reason is almost all of science is in this state. If you think about it, if you're a cell biologist and you're studying something about the cytoskeleton or whatever in the cell, what do you have? You have data and you have horrendous simulations. That's like a standard thing in most areas of natural. If you do climate, you have tons of data, way more data than we have, and horrendous simulations. So all over the physical sciences, or the natural sciences, I should say, people are in this state where they have data and horrendous simulation, and that's what's driving a lot of research here. And this might end up being, like in 2 years or 5 years at this, summer school might be all about this. Because lots happening there very fast. Partly because it's driven by a real change to the world. Yes? Approximate Bayesian computation, which I hate to expand that because every Bayesian computation is approximate. So it kind of pisses me off that they adopted that name. MCMC is approximate Bayesian computation. But anyway, there is a technical meaning for approximate Bayesian computation, which is a likelihood-free inference. It's a way to compare simulations to data. Okay, good. I put that in parens because I'm not going to talk about it. I'm just giving you the keyword so you can look that up if you want to go down that path. Many people are in that state, by the way. Okay, good. So what is another option? So another option to do inference in this case is to boil the data, the huge data you have, down to a tractable set of summary statistics, and then try to do inference on those summary statistics. See, if we could make the data much lower dimensionality, we could possibly get to a state where we can actually do inference. Because then we would be able to do enough horrendous simulations to sample the density in that space, and we would be able to do MCMC in a finite number of dimensions or whatever. So, and that is the path that we take. So the path taken in large-scale structure is to build summary statistics. So that's what we're going to do. So I'm going to talk about how we construct those summary statistics. But I'm going to talk about how we construct those summary statistics very generally. The actual story, the true story or the full story of how you compute accurately like a correlation function given a set of points, how do you accurately compute a correlation function, which is going to be one of our summary statistics, is that would take all 5 lectures. There's so much detail in how this works because the data are dirty in various ways, and the statistics are sensitive to certain kinds of problems. So a lot of work has gone into computing these statistics well in astronomy. There's a huge literature on this, in fact. There's probably 500 papers on details about how you compute accurate summary statistics from a set of data or from a horrendous simulation. because of course we're going to build those same statistics out of the simulation as we do out of the data. This is a very interesting subject. The nice thing is that these summary statistics can respect our symmetries. And this keys into a point I made on the first day, which is that you have knowledge. You have a lot of knowledge about your problem that you're working on. You should capitalize on that knowledge when you're working on your problem. So we could make arbitrary statistics from these data. That would be stupid. We want to make statistics that capture our beliefs about the data. And for instance, we believe that the universe is like rotationally it's invariant to rotations and it's invariant to translations. The statistics should have the same invariances that we believe the universe has. And so we're going to build statistics that respect our symmetries or our beliefs about cosmology so that when we are doing our inference, we are not wasting time in the inference on aspects of the data that we think are irrelevant to cosmology. Now, in other part of my life, I actually test the question of whether the universe is homogeneous and isotropic and so on. And then we build different statistics for doing those kinds of tests. But if what you're doing is measuring the cosmological parameters, you're doing it within the context of a model, and that model is homogeneous and isotropic. Yes?
Isn't it true that our direct observational data is not actually, as it were, translationally invariant? Because as the farther out we look, the farther back we're looking. So if we look at a different time in the history of the universe, we're going to see a materially different universe.
Good. The question is about whether in any actual observation is not rotationally and translationally symmetric. That is absolutely true. We're going to build statistics that are there's two important factors. One is that the redshift direction is different from the transverse directions because the redshift direction is also a time coordinate, and galaxies further out are younger galaxies, and they're living in a younger universe. And so the statistics we build actually have an anisotropy and deal with the radial coordinate differently from the transverse coordinates. So that's one thing. Actually an even more important effect is we don't survey the whole sky the same way. There's some parts of the sky we look at, some parts we don't look at. Some parts of the sky we look at better than others. Like some parts of the sky have dust in front of them that's obscuring the distant galaxies. Some parts of the sky we happen to observe on nights that the conditions are not as good. Some parts of the sky are near very bright stars, and the extremely bright star blots out the galaxies that are nearby. So there's a huge amount of complexity to the way we observe the universe. So even though the universe, we now can see at very high precision that the universe is isotropic and homogeneous, no observation of the universe is isotropic and homogeneous. And we are going to account for that when we build these summary statistics, or as best we can. Actually, one of the interesting things about this, in order to build these summary statistics, you have to make additional assumptions. So, and I keep focusing on this assumptions, but it's really important that we have to, you never know everything you would like to know in order to make these summary statistics. You can't really know everything you'd want to know. Okay, good. So let me just say a few words about how we construct those summary statistics. And then I'm going to come back to how we turn that into a likelihood function, which we are then going to do inference with. Okay, so fundamentally, the statistics we use we go up in an expansion of statistics, and we start with the mean properties of the universe, and then we go up to the variance properties of the universe, and then if we have a lot of chutzpah, we go to the skewness properties of the universe, and then if you really have no fear, you can go to the kurtosis properties of the universe, though it's very, very hard to measure them. So we're going to do an expansion where we go up slowly and I'm going to talk a lot about variance, but I'm barely going to touch skew, and I won't talk about Kurtosis, yeah.
Kurtosis for me, so I can look it up later.
Good, I will. Why don't I write it right here? Kurtosis. All you need to know is that it's the fourth order statistic.
Thank you.
And skew is third order, variance is second, and mean is first order statistics. So I want to focus on the second order statistics, the variance, because most of the information about the cosmological field comes from the variance of the galaxy distribution, which is sometimes called, if you work in real space, is usually called the correlation function. And I'm a big believer in real space. And if you work in Fourier space, you call it the power spectrum. And the correlation function and the power spectrum are very closely related. They're basically the Fourier transforms of each other. And the correlation function is something about the variance of galaxies in real space, and the power spectrum is something about the variance of galaxies in Fourier space. So you can think about it either way. Everything I say in real space now has a Fourier space equivalent that you could also say. Okay, so more or less, what we do, here we have galaxies. I'm going to now sketch this. It's going to get really strange. So anyway, let's forget for a moment about the anisotropy that we just discussed, the fact that the radial coordinate is different from the transverse coordinate. Let's just, for now, imagine you have a set of points in three-dimensional space, and you want to do a correlation function of them. What do? Well, here's a point, here's another point, here's a point, here's a point, here's a point. I'm going to try and make them fairly clustered. Galaxies do actually look very clustered like this. They don't look like a Poisson sampling. They don't look like random distribution of points in space. They're much more likely to see nearby pairs than you would if you just had a uniform Poisson sampling of galaxies. And that's, of course, because there's been gravitational clustering from the initial conditions. So what is the simplest two-point statistic here? Or what's the simplest way to kind of measure the clustering? So the simplest, there's several things to say. One thing is we want a measure of the clustering that is rotationally invariant. Meaning, if I make a measurement of the clustering here, I want to be able to take this distribution, rotate it, and if I made the same measurement, I'd get the same answer. See what I'm saying by rotationally invariant? It's not assuming that the distribution is rotationally invariant. It's assuming that the statistic that we create from it is rotationally invariant. Similarly, if you go up to third order statistics, when you have third order statistics, so when you do second order statistics, we're going to be asking things about pairs of objects, about the separations of pairs of objects. When we go to third order statistics, like skewness, we're talking about distributions of triples of objects. And once you're looking at triples of objects, you're producing triangles on the sky. And those triangles have shapes. The assumption is not that the triangles are all equilateral or something. No, the different triangles are very important. But the triangle this way and the same triangle this way is the same from the perspective of our statistics. So the rotational symmetry is not that we ignore all angles. The rotational symmetry is that we ignore the overall angle of the figure and only consider the internal angles of the figure. Does that make some sense? Yeah?
Yes. The large-scale structure size of objects, the skewness is small, right?
Yes, on large scales, the skewness is small. In fact, so we now know very accurately that the initial conditions of the universe have almost no skewness. The initial conditions of the universe to very high precision are perfectly Gaussian, which is very interesting. And of course, it's been used as a support for the kind of quantum fluctuations inflation origin.
You just haven't gone nonlinear. That's
right. It's as the structure, and in linear growth. So if you just create very, very low amplitude fluctuations that are perfectly Gaussian, and you let them grow a little bit, they grow into slightly larger amplitude, perfectly Gaussian fluctuations. But when the clock goes large enough that dark matter particles start to orbit each other, then that would be called nonlinear in our business, when they start to have curvature to their paths. Then you're going nonlinear, and at that point you get skewness and kurtosis and everything else. But one of the reasons people hope that in the long run we might be able to do true inference all the way back to the data is because on some scales the data look very Gaussian. So if the data were, and in the cosmic microwave background, the data are extremely Gaussian because that's very early universe when things are still very Gaussian. And in the cosmological, in the CMB world, people have been able to do principled inference all the way from the cosmological parameters right to the data. Because in that case, you've got Gaussians to protect you. You have a lot of applied math you can use. But the most interesting cosmology, of course, is happening at the place where the universe is becoming nonlinear. At the place where the universe is fully linear, it's all kind of solved in the CMB, or much of it is. In the place where the universe is extremely nonlinear, like there have been many orbits, we can't compute anything accurately. And so the sweet spot is right when the skewness is starting to become important. That is the sweet spot. So that is why these next order statistics are really valuable in cosmology right now.
So at what point in the evolution history of the universe does the dark matter halo start spinning?
Well, this curvature happens of the trajectories happens on different timescales and different scales. Okay. So very, very small objects go nonlinear very early in the universe, and very large objects are going nonlinear now. Okay. So the very largest structures we see are kind of going nonlinear now. The Milky Way is in a dark matter halo that is of a scale that went nonlinear, I don't know, a few, like less than 1 billion years after the Big Bang. But so it depends on scale. It's very strongly dependent on scale. When you have to worry about this curvature. And so one of the things that's very nice, if you take a large-scale structure survey like this and smooth it on very large scales, like you just average the total galaxy density on some big scale like this, and you run around the survey averaging it, the field you get is basically a Gaussian random field. It's very close to Gaussian. It has very little skewness if you do it on a big enough scale. And then you can actually do completely linear inference in cosmology. And that unfortunately is all kind of fully exploited scientifically. So now we're working at the nonlinear scales.
I think I have a basic confusion.
Yeah.
Is there a way to do inference without building summary statistics? Would you always have to choose something?
Well, you mean in this context or in any context?
In this context.
In this context right now, no, but it's because there are 10 to the 6 galaxies. In the solar system, so imagine you take the 8 planets of the solar system, and there you could do complete Bayesian inference on everything, because you only have a 48-dimensional, well, there's the sun too, so whatever, a 54-dimensional parameter space, which is the initial condition of the solar system, and you can fully do inference in that initial condition set. And you don't have to make any summary statistics at all, you can just do it all.
So I get this is specific to this context, I suppose, but don't you want statistics to kind of like wipe out, chance peculiarities?
Good. That's a great question. The question is, it's great that we're doing summary statistics, but don't you kind of have to in this case because you want to wipe out certain kinds of particular aspects or phases? So that is true. That's a very good point. In some sense, very important conceptual point. Many cosmologists, when I say we would like to do inference at this level, meaning just directly write down a likelihood function for these numbers, many cosmologists, professional cosmologists, straight up disagree with me. Because they say most of the information in these numbers is totally uninteresting. Like we can measure the RA and DEC of a galaxy to 10 digits of accuracy each. None of that matters because you could just rotate the universe slightly. They'd all have completely different RAs and DECs and you'd have exactly the same universe. So one of the things that the summary statistics is doing here is wiping out tons of the peculiarity of our universe that we don't care about. We don't care about the orientation of our coordinate system. We don't care about where we are currently sitting. Like the solar system the Milky Way is here in this large scale structure and we're looking out at it. If we'd been over here, we would be still seeing the same large scale structure. So it doesn't matter, our viewpoint doesn't matter. And so we're going to make these statistics to wipe out these uninteresting things, which is about our viewpoint, angles, and then of course also the details of the initial condition. The initial conditions are delivered in a kind of power spectrum sense. Any individual realization of them has a set of phases about like where exactly the peaks and valleys are, which are uninteresting to the theory. Good. So that's a very good point. It's not just the case that we have to go to summary statistics computationally. Intellectually, you kind of want to go to the summary statistics because they integrate out a lot of the things we don't care about. That's right. I still think we should go up, but you're very right that we don't have to in general. Yes?
Some of the things that you mentioned that like you could do to make things easier for the interpretation could also be done on the data, so like pre-processing of the data, like you rotate things into standard frames, this kind of stuff. Do you have an opinion? I mean, as a statistician, would you rather have that in your analysis, or do you want experimentalists to do that and make your analysis much easier?
Good, that's a great question. So in this case, we are, in some sense, constructing these summary statistics is a pre-processing of the data. From my point of view as an inferer or parameter measurer, like in my role as somebody who measures parameters, I see all of this as a pre-processing step. That is exactly what I see. Of course, I've also spent part of my life in this role, and then I see this as making cosmological measurements. So like different people talk about a cosmological measurement differently. If I'm in this role, I see these as the cosmological measurements. If I'm in a role of trying to understand what's the, I don't know, the slope of the power spectrum, so the slope of the initial conditions, you know, the running of the index of the scalar, whatever, then I see this as a pre-processing of the data. Good. So that is one way to think about it, and that also is related to your question. That in some sense we're pre-processing the data to get rid of the parts of the data we don't care about. And my only issue with that as a statistician is I worry that maybe there's something interesting in the data that's getting run over. That's why I don't like the pre-processing, and I wouldn't do it if I didn't have to. But there are other cosmologists who are at least as reliable as I am, who would say the exact opposite. Good. Where are we? Yes. So fundamentally, so let's talk about the 2-point statistics first. So in the 2-point statistics, you're talking about separations. Here's galaxy I, here's galaxy J, and there's separation Rij between these two galaxies. My I looks like a galaxy, my J looks like a galaxy, but anyway, you'll figure it out. Fundamentally, the 2-point statistics of the galaxies is about the distribution of these Rij values. So in some sense, what we do when we do the correlation function is we ask, what is the ratio of instances of this radius to what you would get in a universe that had no clustering? So we imagine a fake universe that has no clustering. Galaxies are just laid down Poisson, and we ask how much more likely or less likely is this separation of galaxies than what you would have gotten in a universe with clustering? That is fundamentally the question. And the statistics of those excesses, of the excess numbers of galaxies at certain separations, those statistics are the statistics we move forward into cosmology for inference. And the nice thing is the statistics that we're going to write down obey good symmetries. So let me keep going on that question. So now imagine, let's just zoom in on that. Here's galaxy I. And now let's consider a spherical or cylindrical, depending on how you want to think about it, volume that is at radius r and has width dr or delta r. Good. So at radius r and width delta r, you can ask in the survey how many other galaxies happen to hit inside that cylinder. And then you can ask, how many would have hit inside that cylinder if the galaxies had been distributed uniformly throughout the universe with no clustering? The same number of galaxies. Remember I said we're going to do 1-point statistics, 2-point statistics, 3-point statistics. Here's a 2-point statistic, but it does depend on the 1-point statistic because we have to know how many galaxies would have landed in that annulus if we had no clustering, which means if we had the same mean density, the same 1-point statistic, but no interesting 2-point statistics. And that is the correlation function. The correlation function is the ratio, more or less, of those two things. The correlation function C of R is defined to be excess number of galaxies at R relative to unclustered. And the way we, in fact, construct this statistic, so as I said, this correlation function is going to be a summary statistic of the data. And the way we construct this is we count pairs. Literally, we go to each galaxy and we ask how many pairs are inside this annulus. And we do the same thing for a mock catalog, which has no clustering whatsoever, and we compare the counts in those catalogs. So it's count pairs in data and in what's called in the business random catalogs, which is a really bad name. They should be called unclustered catalogs.
I got a dumb question.
Yeah, hit
Why
me.
do you need a catalog? It sounds like there should just be an analytic solution for the
Good. Great question. You're like leading right into my next topic. The question is, why do you need a random catalog? Why do you have to count pairs in a random catalog? Shouldn't there just be an analytic prediction for how many pairs there are? Absolutely, there should be, except that the survey we're operating is a real-worldy survey that has all sorts of real-worldy problems with it. Like it is a funny shape on the sky. There are patches where we weren't able to observe. There's places where bright stars blotted things out. There's places where our photometric calibration went out, or we missing a band or something. There's a lot of different things that happen. Some nights we took spectroscopy and we were clouded out, or only some of the objects got redshifts and some didn't, and so on. There's all sorts of real-worldy things, and we try to apply those same real-worldy problems to the random catalogs as well as to the real catalogs. So we really are asking, in an unclustered universe that is observed the same way that our universe was observed, what would you get? Does that make sense? And that kills the analytic aspect of the problem. So this is important point, taking into account the mask, which is like where on the sky you looked, the data quality, meaning there are some patches of the sky where certain kinds of galaxies weren't observable, and there's other patches of sky where they were observable, and we have to keep track of what fraction of the galaxy population was observable in the different parts of the sky. And then there's something called incompleteness. And there's several kinds of incompletenesses, but one kind of incompleteness is you tried to get the redshift for the galaxy, but you failed for one reason or another. And there's others where you didn't even try to get the redshift because of some mechanical issue. For instance, in Sloan Digital Sky Survey, if we take a spectrum of this galaxy, we can't take a spectrum of a galaxy that's arbitrarily close to it without doing a second pass. So some parts of the sky got a second pass and we picked up all the near neighbors, and other parts of the sky didn't get a second pass, so we didn't. And that is a very non-trivial. If you really follow that one down, there's something like 20, that problem is called fiber collisions. There's about 20 papers on that problem alone because it's such an intractable problem. Because if you think about it, your ability to observe the galaxy depends itself on the clustering of the galaxies, which is what we're trying to measure. See, there's some like badly circular reasoning that comes in. Yes, hit me.
If you apply these kind of things to your random catalogs, and then you take
Yeah.
the ratio to uncertainties associated with those cancel?
The question is, if you apply issues with your mask and data quality and incompleteness to your random catalog, does it cancel? Do any uncertainties in those things get canceled out? The answer is no, they don't. If you are wrong about these things, you get wrong answers. So a lot of the challenge, so I work a lot of my role actually in large-scale structure projects is something that you might call calibration. So I try to understand very accurately these effects from a kind of data-driven perspective. I do a lot of that work, which is very kind of dirty work in astronomy. But it's really critical because if you're even slightly wrong about this mask, for instance, you think you observed in this location, but you didn't. And sometimes you really don't know that you didn't because there's a bright star and you think you can detect galaxies close to the bright star, but you can't. So really there's a hole in your survey here that you don't know about. It really affects the statistics, and it can especially affect high order statistics when you get to the 3-point function and so on. It's very highly affected by wrongnesses here. And you might think, oh, well, you can just look, where did you look, or whatever. But it turns out it's really non-trivial question at the end of the day, exactly what this mask is. And the other thing that is very hard to work out is what the incompleteness depends on. So sometimes you've observed a galaxy, you took its redshift, and you couldn't determine the redshift for one of the, you got 600 objects in this field, you got redshifts for 599 of them, you didn't get one of them. You don't know why you didn't get it. Did you not get it because just purely randomly, like there was some problem with the data, or did you not get it because it has some spectral property such that you weren't able to measure the redshift, and then that changes something about like your mean density? Like, different choices about that have different implications for what your mean density beliefs are and so on. So, so these things do not cancel out in any sense. They actually have to be right in both cases. Yes?
Related to the incompleteness, how do you deal with it? You were talking about the galaxies that are very close together. Well, at what point do they stop being very close together and become a single merged galaxy?
Good. Another great question. Good. Good, a great question, which is the fact, and when galaxies get very close together on the sky, at some point they will be called one galaxy. How do you deal with that? That is a very big set of unsolved problems in cosmology. That's also something I work on. I work on data, the imaging analysis that goes into these projects and selects the galaxies. And there's two aspects to this problem. One aspect of the problem is galaxies there really are a lot of galaxies on the sky that are in fact merging. They're now are becoming a galaxy. But there's also chance alignments. Once you have a million objects, you actually get tons of chance alignments where one galaxy is in front of the other one, and they just look like they're one galaxy when in fact it's two. These effects at the present day we deal with entirely kind of in the incompleteness part of this problem. And it's all done basically with kind of attempts to model that heuristically. But because we don't have a fully worked out model for how galaxies form and what they look like, we also don't have a fully worked out model of how you separate two overlapping galaxies in imaging. Those are very related problems and they can't be separated. And because we can't do the first problem, we also can't do the second. And I spent a lot of time actually working on that. It's a very hard set of problems, yeah.
Shouldn't your redshift distribution be binodal then in that case?
Good. There are, one of the things we're always looking for is data-driven ways of dealing with weird kinds of inconsistencies. And so we do a lot of work where we try to understand spectra we take as sum of two spectra, sum of two spectra we've taken otherwise, and sometimes we can split pairs that way. Also sometimes there's another kind of bimodality that's very related, which is that fiber collisions thing I mentioned. When you get two galaxies that get so close together you can't take both spectra, some fraction of the time those galaxies are actually close in three-dimensional space, and some fraction of the time they aren't. And one of the things we work on is to try to build kind of data-driven models to understand when they're close and when they aren't. Because you can imagine you do different things in your clustering analysis if you believe they're close or if you don't believe they're close. There's a whole bunch of kind of detailed stories there. But almost every sentence I'm making is like a PhD thesis that's happened in the past, or sometimes a set of them. So like I'm really compressing a lot of the world into a few minutes here. Kind of the point here is to kind of describe, in the first 3 lectures, I kind of talked about like the ideal world, the world where there's rainbows and unicorns and they bring you all the things you need. All the forest creatures help you in your inference. In the real world, all the forest creatures are out to get you. And you can't afford to do what I said in the first 3 days. So you try to build summary statistics, and even building the summary statistics turns out to be an immensely difficult problem because there's so much stuff going on that is between you and your data. Yes?
Is the statistic a function of just the radius of the annulus or a function of the redshift?
It is a function of both radius and redshift. So what we actually do is measure projected. We measure this statistic projected along the line of sight in redshift bins. So we go to redshift bins, project along the line of sight. We need to project along the line of sight because of the anisotropy, that the redshift direction is very different from the transverse direction, and we need to bin it by redshift because in fact it does evolve with redshift. And the random catalogs, though they are unclustered, they do contain the redshift dependence of the original data because otherwise, you detect the evolution in redshift as a huge clustering signal, a huge radial clustering signal radially away from the Milky Way. So yes, all of that has to happen. Good. Now, that is the 2-point function. This is the 2-point function. Fully describing the 3-point function now would be a lot of work. But let me just say that fundamentally the 3-point function is the same question, except that instead of asking about annuli, I have to ask about triangles of certain configurations. So I have to consider all the triangles of this configuration, and then all the triangles of this configuration, and then all the triangles of this configuration. You see, and it gets combinatorically challenging. So the 3-point function measurements that people make are not fully general, because fully general, you'd have to have too much, you need more data than we have to measure a fully general 3-point function. So what we generally measure are certain integrals of the 3-point function. So the 3-point function for only triangles that have certain ratios of side lengths, or triangles only in a certain size range or something. We only look at slices or integrals of that 3-point function because measuring the full 3-point function, there just isn't enough data to measure the full 3-point function. Yes?
Is it specific to LSS, or I guess you can do it for CMB, like in
Yes, the question is about LSS versus CMB. Yeah, the 3-point function has been measured for the CMB as well, and it basically vanishes. Well, vanishes in the sense it has exactly the value you'd expect under the Gaussian field. There is a little bit of residual in the CMB, but we think it's coming from foregrounds. Because of course the CMB, you don't just see the CMB, you see it through the galaxy and you see it through the universe, and those foregrounds induce some 3-point statistics. But yes, you can do 3-point statistics on any data, but as you go up in order, they get harder and harder to measure. In general, for 2 reasons. One is that just the simple reason that it's harder to measure a skewness than a variance. Like just if you had a set of points in 1D, you have a noisier measure of the skewness of those points than you do of the variance. So that's one thing. But the other thing is you get these configurational factors. So now I have to consider all triangle. Here I only had to consider all radii. That's 1D. Now I have to consider all triangles. That, if you think about it, is 2D or 3D, it's really 3-dimensional, all possible triangles. If you go to the 4-point function, it gets harder to measure, and you now have 4-point figures, which is, I can't even calculate, 5D? Oh, in 2 dimensions it's 5D. Anyway, I don't know. It's something really bad. It's bad in what all the things you can do with the 4-point function. So as you go up in order, it gets much, much harder. And one of the things that's going on in cosmology right now is trying to find new statistics. And a lot of work is going into that. How to find statistics that are well measured, but sensitive to interesting things. Well measured, respect our symmetries, but sensitive to particular physical effects. So one example that's going on right now, and there's a literature appearing like every few weeks in archive, is about the neutrino mass. So cosmology, large-scale structure experiments are just becoming sensitive to the total mass in neutrinos. The total mass of neutrinos has an effect on cosmology because they're effectively a dark matter component that is hot at early times and cold now. And so it has a different effect on large-scale structure than the cold dark matter. So it is just becoming visible in large-scale structure surveys now, but it's a very subtle effect. So people are trying to find statistics, summary statistics of cosmology experiments that are very sensitive to the neutrinos, but respect our symmetries and are possible to measure. And that's kind of a very hard, if you think about that, that's a very hard problem because there's a combinatoric set of statistics you could write down and you want to find the one that's best. And so that's a kind of interesting area. And in general, if you encounter hard data analysis problems, there's going to be this question of like, how do you choose your summary statistics? And in cosmology up to now, we've chosen them more or less heuristically, but in the future, we might choose them using robots, which is another thing I'm interested in. Yes?
When you do the variance, the 2-point, are you doing a flat ring, or is this actually like a spherical shell? Are you making that the axis?
Good. The question is this a flat ring or a spherical shell? It depends on what scale you're working at. So I generally work at small enough scales that the redshift differences are unreliable and the transverse distances are reliable. So we generally project slices of the data down on the redshift direction and just work in 2D rings. But if you work on very large scales, which I do when we measure like the homogeneity of the universe, we work on very large scales, and then we do spherical shells in the implied 3D space. So it depends on your problem, what you do. Okay, good. Now, oh, good. Things are on. For once, I'm on target. Okay, now now what we do is we count pairs. We do all that with respect to the random catalogs, and what we end up with, we take this enormous survey, which took 10 years to produce, and 250 people, and hundreds of PhD theses, and we produce like 12 data points that look like this. I mean, it's still more than the mass of the Higgs, but what? On some log plot. So this is like log R. This is log of that radius, and this is log of that correlation function, and we get some points like that. Now what? I did something here which is strange, which is I drew error bars on these points, or uncertainties, and you should ask, where did those come from? And I'm about to say, because that is going to be in some ways the most challenging thing of all of this. And the idea is that any theory, these horrendous simulations we do, any horrendous simulation can be taken, that horrendous simulation can be taken, and it can be put into the same mask. We can apply the same data quality censoring to it. We can censor it again with our incompleteness, and then we can make exactly the same measurement from any horrendous simulation. So we have the data here, and then we have the same plot for a bunch of simulations. Simulation A, simulation B, and so on, all the simulations. So that we made this data plot, and then we make a set of simulations. Yes?
So for one of the people of fundamental theory, how stable are these distributions for different simulations?
Good. So that is exactly why we have to do many simulations, to understand what the stability is. And of course, the real answer to your question depends on the size of your survey and what scales you're working at and all sorts of things. So, but the current precision level at which we're doing these experiments is like 1%, meaning that the variance across simulations of this experiment, of this sort of overall shape of this is of order 1%. But the only way we can determine that is by doing many simulations. There are theoretical ideas about how big these uncertainties should be, but they're only order of magnitude estimates. If you actually want to understand the uncertainties, you really have to do many simulations. There's another issue, which is that neighboring points in this correlation function are correlated. These are not independent measurements. And the reason they're not independent measurements is that you are laying down overlapping annuli. So at some point I'm going to be measuring this point with a bigger radius, and it's going to see those 2 points. So the counts in this annulus are not independent of the counts in that annulus. And so in general, the different radii are correlated in the data. So it's not just the case that you have a set of data points where you don't know the uncertainty properties, you know they will be correlated.
Did you see where the error bar came from?
Say again?
Did you say where they
Not yet. So really I should draw this without error bars at this point, because all we've done is produced the simulation. It's produced a statistic. We don't know its uncertainty properties yet. We're going to determine its uncertainty properties with this set of simulations. That's the idea. Yes?
Don't you have already a built-in uncertainty because your R is going to scale with how far out you're looking, and the angular distance across the sky depends on you've got your angular diameter distance. So you have your uncertainty in that separation.
There are, in addition, so the question is about uncertainties and what comes from the uncertainties in the measurements. In addition to there's two kind of sources of uncertainty. There's kind of uncertainties in the measurements, in some sense, like how well do you know this R? And there's uncertainty in the sense that these data, so in some sense, these measurements in the data are somehow perfect. Because it turns out in most cosmological experiments, the uncertainties of our measurements are tiny with respect to anything that's going on here. We measure redshifts extremely precisely. We measure positions on the sky extremely precisely. So in some sense, there's no uncertainty on these data because it's just really well measured. It's just a fact about the data. This is a summary statistic of the data. It's like just a rotation and integration of the data in some sense. So in some sense, this is just the fact of the data. But when we draw uncertainties, what do we really mean? We mean how precisely do we expect these to meet an expectation? And that uncertainty we can only determine by doing simulations. Yes?
I think this data looks quite different from usually we will see from the large-scale matter power spectrum. Or is this just a part of that after Fourier transformation, or is it whole data?
The question is, how does this relate to the power spectra you've seen? This is literally a Fourier transform of the power spectrum if all your estimators are correct.
Yeah, but we see there's much more data when we see the matter power spectrum.
Well, in principle, it's exactly the same data, but it is true that it looks very different. So a very good example is the CMB. If you go to the WMAP paper that was the original, like the first CMB experiment where we really saw the multiple peaks in the CL spectrum, in that same paper, they also show you the correlation function of the data. And it looks like this, And in fact, it's exactly the same information in this plot that does this, and this plot that goes, But it doesn't seem like they're the same at all, but they are the same. It's literally the same information. They're just being shown in different coordinate systems in a certain sense. describe these projects in real space in part because I think it's easier to describe, and it's also easier to think about these problems in real space than in Fourier space. But the exact same set of operations can be done in Fourier space. What does it look like in Fourier space? What you do is you project the data onto sines and cosines, and you project the random catalogs onto sines and cosines, and you take ratios of squares of those projections. You take ratios of products of those projections, and that produces your power spectrum estimate, and then the power spectrum estimate is also something you could write here. But once again, in order to get the uncertainties on it, you do the power spectrum in the simulations. The different points in the power spectrum are correlated. It's all the same story in the power spectrum. So I'm just writing it this way because it's the way I think about it, but all of this carries over to the power spectrum. And it is the same information in principle in both places. If you do the data analysis correctly, in principle it's the same information. The fact is, of course, there are small differences in what people learn from the power spectrum and from the correlation function, and it's probably because there's some issues in how we deal with this kind of housekeeping data. Yes?
So if you wanted to convert this to power spectrum, you'd have to start from the correlation function and redo the whole analysis, or could you just go from that conclusion plot and do a conversion from the summary statistics? In principle, you could do a conversion from the summary statistics, but in general, that's not a good idea because details of like how you bend these annuli will project into the power spectrum in weird ways. So really, you want to go back to the original data, and instead of counting the excess number of galaxies, blah, 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 you're going to look at the excess projections onto the amplitudes of sines and cosines in the. And so you really want to go back up to this state and re-estimate, do a different estimator. Actually, that's a very interesting thing. We've convened some meetings where we've had applied mathematicians talk to cosmologists, and the cosmologists will say things like, well, this is just the Fourier transform of that. And the mathematicians will be like, no, they're not. They're like, yes, that's the definition, says the cosmologist. And the mathematician said, if you're working in continuous function spaces, which we're not. We're always working in weird binned pixelization type things. And so there's actually there's a lot of physicists work in like heuristic math, you know, where the Fourier transform of this is, like we know Fourier transform pairs. None of those Fourier transform pairs are correct in any finite data set with any finite pixelization, with any finite mask, or all those things kind of fall apart. And so there's a lot of subtleties about you really have to, in these projects, you really have to decide very early what basis you're going to work in. Yeah?
If we just take one of these points,
yeah.
Is there some information about the parameters of the theory that can be learned from just the sample variance? Meaning, you look at the simulations of, say, one of these points.
Yeah.
Does the spread depend on the parameters?
It does. The question is about the spread. So this data, the data have some value here. The question is, the sample variance among the simulations that you might have here, does that contain cosmological parameter information? It does. Different cosmological parameters affect both the heights of these points, the expected heights, and the variance you expect for these points.
So follow up to that. Is it then possible to exploit large-scale uniformity of the universe to, instead of getting one data, can we get multiple data for each of these points?
So one question is, exploiting the homogeneity of the universe, could you make, say, this in different locations in the universe and get different, and look at the sample variance around different parts of the universe? Yes, you can, and people do that. And in fact, it's a very interesting subject right now to ask whether the cosmological parameters over there are the same as the cosmological parameters over there, because it connects to questions in inflation, right? Because if we collapsed to some arbitrary vacuum, maybe there's a continua of such vacua, and maybe it's slightly different over there than over there. We should figure that out. So people are interested in those questions, but it's important to remember that if you look at the variance of a 2-point statistics, you're looking at a 4-point statistic. And so you quickly run out of data. as you start to try to do that. If you ask detailed questions about the variance of, this is a variance in some sense of the data. If you look at variance questions about the variance, you really quickly run out of data. And that's going to happen here with our simulations. It turns out to do what we want to do, we need more simulations than we can possibly run. I'm about to tell you, in my last few seconds, I'm going to tell you what we do with the simulations. Okay, so because all we've done is we've constructed a summary statistic of our data. We have a summary statistic, here it is. It's some set of data points, but it is much smaller than our original data. So we have compressed the data, and we've used a lot of our knowledge to compress the data. We've used knowledge that the universe has kinds of symmetries, so we used rotationally symmetric quantities, and we used a lot of our knowledge about the dirt in the data. So we've made a very, very nice summary of the data, but we are not doing cosmological parameter estimation yet. How do we do parameter estimation? Well, if we call this data y, this set of points is a vector y, now we can ask, what do we get in the simulations, and how do we construct likelihood? We need to have the probability. Sorry, I'm switching boards on you again. We want to write down, we want P of y given theta. Notice that this is a pretty limited goal. We're not asking for the probability of the whole data set. We're only asking for the probability of the summary statistic. Given these will now be the cosmological parameters. And plus, I should say, it's cosmological, that's supposed to say parameters. The cosmological parameters and some parameters about galaxy formation, right? Because these simulations are not just cosmological simulations, they are also galaxy formation. They have to place galaxies into the simulation as well, because the summary statistics were made on a galaxy survey. Now, imagine you were able to do tons of simulations. Tons and tons of simulations. Then you see at every point theta, you could do a whole bunch of simulations and find out all the different y's you could get. And then you could move to the next point in the parameter space, and you could do a ton of simulations and figure out what distribution of y's you get. And then you could move to the next, and do it, and the next. You see how you could just empirically just figure this function out? That takes a lot of simulations. Why does it take a lot of simulations? It's because this space has the same dimensionality as the number of points we measured over there. So I only showed like 9 points, but typically we would do something like 20. But this is of order 20 dimensional, let's say. And this parameter space, cosmological parameters, there's like 6 of them. Galaxy formation, you have to throw in a few more. So if you're really, really lucky, you might be able to have this as small as 9. But you see, you're trying to figure out a 20-dimensional distribution or density as a function of something like 9 control parameters. See? And if you think about that, that's a lot of simulations. No one has ever been able to do that many simulations. And so in practice, so good, in principle, use many simulations. Use many simulations to learn this function. And that is this is what people are working on in cosmology. So there's big projects coming up now, very big projects that are very well funded and very well thought out. One of them is the Euclid mission, which the European Space Agency is going to launch, which is a very big cosmological mission. Another mission is LSST, which is a ground-based project that is going to be the largest astrophysics project or optical astronomy project that's being done by public entities. And then there's going to be WFIRST, which will be a NASA mission that will do cosmology. So there's a bunch of these projects that are doing very big surveys, and part of their budget is to do enough computation to learn this function. That is what people are working on, and there's a lot of interesting and good thinking about that. In practice, right now, we do not have enough simulations to do this. So in practice, we use simulations to determine a covariance matrix. What do I mean by a covariance matrix? We look at the empirical, say we have M simulations. We look at the empirical Y. This is Y from simulation little m minus some mean of such simulations. Ym minus mean transpose, that's an outer product, sum over m, that's a capital M. The idea is you do many simulations, you take the mean of those simulations, and then you take the outer products of the differences from the mean, and you see that makes a covariance matrix, an empirical covariance matrix. We use that empirical covariance matrix in a Gaussian function, and that's what we do, because that's all we can afford to do. And we're literally, even this takes a lot of simulations to get a good solid estimate of this covariance matrix. It takes a lot of simulations. So we do that and use a Gaussian LF. So it's a little embarrassing that at the end of the day, we just assume that the likelihood function is Gaussian. We do a bunch of simulations to determine the variance of that Gaussian, and then we do some set of simulations to find the mean of that Gaussian. How the mean of that Gaussian depends on the cosmological parameters. So that's all we can afford to do. And this, if you look in the statistics literature, this method is called surrogate. Surrogate likelihood function. Interestingly, the cosmologists do not call it by this name because cosmology has been doing this since before they noticed that there's a statistics community. And the statistics community has been doing this since long before the cosmologists crossed their radar. In fact, probably before the cosmologists even thought this up. It's been being done in statistics because there's many problems in statistics where you can't write down the likelihood function. So you do something sensible to come up with a surrogate function that replaces your likelihood function, and you do your inference with that. And that is what we do in cosmology large-scale structure projects. And that is the dirty laundry of my business. I'm done.